Hey, what's happening, ladies and gentlemen? It's Mr. Simkins coming at you once again from the Simkins Physics Corner. For this lesson, we're going to talk about experimental design. How do you design a quality experiment? You see, in science, we're going to make observations with our eyeballs and maybe with our other senses as well. That would be called a qualitative observation, something that we can describe by its qualities. But the most effective argument that we can make is one with data. Say, hey, here are the numbers, here's what I measured. That's called quantitative data. And in order to get quality quantitative data, you have to conduct a quality experiment. So today, we're going to talk about the steps of the scientific method, which are over there on the right. We're going to go through some key terms about the things we need to think about when we design an experiment. And so as we walk you through here today, the goals are to know the scientific method by its steps, know what each of those steps entails, how to conduct each of those steps to a high degree of quality, and then what these other terms are and how they come into play as we design a quality experiment. So let's hop right into it. All right, the first part of the scientific method, of course, is what are we going to explore? So the question or the purpose, it will be called sometimes, it identifies what you are investigating. I'm going to go through an example here in a minute about what these steps will look like, but that's very straightforward. What are we investigating? That should be addressed in your purpose or your question. The second part is making a hypothesis. All right, now some people call it an educated guess. I have a little bit of an issue with that definition. I like to say this way, based on research, because some people will say the second step is do research. Based on research or prior knowledge, maybe we've already explored this a little bit, what is a sensible outcome to expect? All right, and so again, I'll flesh out what these would look like in the example we're about to reach in just a minute. But the hypothesis is basically, hey, based on what we know or based on what we just learned, what do we expect to happen as we investigate this question? Then you're going to get to the experiment, and this is the meat and potatoes of the experimental method. If your experiment is not of high quality and it's not well designed, then your data is going to be garbage, and your conclusions based on that data are going to be garbage. All right. So experimental is a methodical, careful investigation of relationship between two variables. All right, so let's get into the details of what that means. What two variables? The independent variable and the dependent variable. Now, the easy way to remember the difference between these two is the independent variable starts with an I, and the independent variable is the one that I change, or whoever is conducting an experiment. If it's you, that's the undependent variable. That doesn't sound as good, does it? The independent variable is the variable that I change in order to observe that change's impact on the dependent variable, and that's going to depend on what we did with the independent variable. So the dependent variable is the one that we measure to discover its relationship to the independent variable. So at this point, you may be like, oh, whoa, okay, I got these new terms flying at me. Can you give me an example of what that might look like? Sure, let's do it. I have a 2-year-old son. He loves Matchbox cars right now. So let's take a look at these two little peeps. They're having some real fun, and they have a little ramp. So they have a ramp, and they're sending their Matchbox cars down these ramps. Looks like they're having a little race there. Oh, what fun it is to ride. So the two kids want to determine the impact of changing the angle of the ramp with respect to the average speed of the cars. So these two little physics geniuses, I mean, look at them. You know they're asking this question in their head. Hey, if I change the angle of the ramp, how does it impact the average speed of the cars? Well, those are two variables, and they're going to design an experiment to explore the relationship between those two variables. So if we circle back for a second here, our question would be, how does changing the angle of a ramp impact the average speed of a car? That defines what we're doing. Hypothesis, all right? I don't need to research this one. I can say, well, my hypothesis is that as the angle of the ramp increases, the cars will go faster, right? That's something that is based on prior knowledge. It is a sensible outcome to expect. And so I state that. I say, I'm going to investigate this, and I imagine that what we're going to see is that as the ramp gets steeper, the cars will go faster. All right. Now let's talk about, in this particular scenario, because it helps to have an example, what are the independent and dependent variables? Well, what's the one that or in this case, the two guys here, what is the variable that I am going to change? I am going to change the angle of the ramp. So the independent variable is the one that you change, is the angle of the ramp. The dependent variable, the thing that we're measuring after change, we're going to measure the first one too, but we're going to measure the impact of changing the angle of the ramp on what the average speed is going to be by the time it travels the whole length of the track. So average speed is going to be our dependent variable. So I hope that you see that there's an independent and a dependent variable. We manipulate the independent variable and we see what impact that has on the dependent variable. In this case, the independent variable, the one that I change, is the angle of the ramp. The dependent variable is the average speed of the car as a result of that change. Okay. Cool, so we're designing a good experiment, but here's the thing. You gotta be real careful when you do this. You need to make sure that you only change one variable and measure the impact of that change on another variable. You don't want other things called confounding variables to enter into this. So what are some things that we would want to control or make sure it's consistent or the same from trial to trial? Well, let's think about this. You see on this picture, they have 3 different Matchbox cars. Well, if I want to know how does the angle change the speed, but I'm also changing the car I use every time, do you see how that's going to enter another variable into the equation? And that would give us less confidence in the results that we end up getting. So what we want to do is control variables, things like where you release the car from, right? What if the kids are being careless and on trial 1 they release it from here, but trial 2 they release it from there? I imagine they would get a different value for speed, don't you? So we have to make sure that we're controlling everything else except the one variable that we're changing and the one variable that we're measuring. So the type of car, we want to use the same car every time. The method of timing. You don't want to use like a high-tech stopwatch that's really sensitive and accurate for the first 3 trials, and then be like, well, that battery ran out, so I guess I'll use my phone for the other 5, right? You want to make sure that you have a consistent method of timing. So all of these other things, you want to think about, okay, I got to make sure that everything is consistent except for the independent variable that I change and the dependent variable that I measure. All right, so that's what we mean by control variables. We mean all the other things that we want to make sure don't change, because otherwise we have no idea whether we actually discovered a relationship or not. It could have been something else in the background changing the way things are going. In light of designing a good experiment, you want to make sure that you do multiple trials. I have a little statement here, but basically, what do you think would be higher quality? If a little kid timed a car going down a ramp once and used that time as their data point, or if they did that same process 5 times and then took the average of those 5. The obvious answer is, of course, the average would get us closer to the true value of that measurement than just timing it once. And so whether you're measuring time, whether you're measuring distance, whatever you're measuring, you want to do multiple trials at each ramp angle. So it would look like this. We set the ramp at 8 degree angle. We timed the car down the ramp 5 times, and we took the average of those 5 times. Okay? Then we changed the angle to 10 degrees. We timed it 5 times. We took the average of those 5 times. That would get you much higher quality data. All right, so we got to be careful as scientists. We want to be very methodical about how we do this, is what I mentioned earlier. That word methodical, meaning have a good method, being very precise with what we're doing. And in order to ensure that our results are a little more accurate, we want to take the average of multiple trials. All right, so that's what we mean when we say multiple trials. All right, data. Data is where, oh man, I go around the lab, I say that's some beautiful data. Nothing that warms my heart like some data. So data is the quantitative evidence, and quantitative is sharing the same root from the word quantity, or a number, an amount of stuff. So quantitative data is the numbers that we're going to get as a result of doing our experiment. So in our example that we're looking at, our quantitative data would be the degrees of the angle of the ramp and the speed of the cars. There would be 2 sets of numbers that have a quantity, and that is what this would look like as far as quantitative evidence. We're going to organize it in a table, and we're going to graph it when appropriate. And I'll try to give you a hint as to the different labs that we do when making a graph makes more sense or less sense. Let me give you an example of what this might look like. So here, there's a couple things. There's a lot. You should probably pause this slide after you're done watching it and rewatch it again, because for all of our labs this year, this is going to apply. When you have quantitative data, meaning numbers, you got to have it in a neat table. And I'll point out a couple of things. The columns, all right, so this is a column right here. The column has a label. It says, hey, you're looking at the data for angle. And it also has the units for that column. So you don't have to write it in every single box. You can just say, hey, every number that you're about to read is angle in degrees, and then you have all your data below it. Every number that you're about to read is speed in meters per second, and then you have all your numbers below it. So make sure with your data table, you label it, and you have the units at the top. Then let's look at this graph. This is a very high quality graph for several reasons. One, it has axis labels, so I actually know what this graph is of. All right, this graph is a graph of average speed of the car in meters per second versus the angle of the ramp. And so this graph here also has a descriptive title: Matchbox cars, ramp angles effect on average speed. And I mentioned earlier that you want to graph it when appropriate. Sometimes a best fit line is also appropriate, or a best fit curve, which we'll get into down the road here as we do graphing next week. But you can see here a clear pattern. If I take my individual data points, you can see what is happening here. As I increase the angle of the ramp, the average speed is increasing. Oh, you mean a steeper ramp means you go faster? The question is how much faster. I can actually quantify that with a number, and I can say for every angle, or for every degree of an angle that I increase my ramp, my speed would be expected to increase by And now I have a number that I can put to that and make a very convincing case for the relationship between the angle of the ramp and the average speed of the car. Okay. Once we have all that data, we're going to do a little bit of what I just did, which is describe your qualitative observations. And remember, qualitative, that word comes from the word quality, and we have many fine qualities. If I were to describe some of your fine qualities, I would talk about descriptions, right? So qualitative data is talking about descriptions. So when in your analysis for this lab with the Matchbox cars, you may say something like, as we increase the ramp angle, the car traveled faster. There's no numbers involved with that, right? So that's not quantitative, but it is a useful observation, and it describes what we saw. That's what we call qualitative observation. And then whenever possible, now it's early in the year, so we don't know a lot of physics concepts yet, but when all possible, connect your observations to physics concepts. So for something like this, I may just say, well, if the ramp is steeper, then gravity probably has more of an impact on the car, and that's why we saw it go faster on a steeper ramp, right? So I tried to throw some physics words in there. As the year progresses, we'll know more physics, and we'll connect more physics to the lab. But look for an opportunity to do that. Finally, in your analysis, you want to do the quantitative observations. So I might say something, let me go back to my data table. I might say for every 2 degrees, or I say for every degree steeper my ramp was, the car traveled 0.13 meters per second faster on average. You hear all these numbers that I'm talking about? That's quantitative. That has numbers attached to it. And so you want to look for those patterns in your numbers. You could also make an observation. You could say, on average, every time I increase the ramp by 2 degrees, my speed increased by about 0.2 to 0.3 meters per second. So again, that's giving a range of values, but it's still giving quantitative values. So in your analysis, you should have descriptions and link it to the physics, and you should have numbers and link it to the physics. All right. And so for the numbers, you might just say, well, a steeper ramp means that the force of gravity has a bigger impact somehow, and that is why it causes the ramp to speed up faster. Therefore, it has a higher average speed, right? And you can throw your numbers in there to support that. That would be a really quality analysis. At the end, this says report. You'll hear it. You'll see it said as conclusion in other places. You want to make sure your conclusion does a couple of things. You want to make sure you address your purpose. So you should go back to the big question. Go back and your conclusions to say, all right, we set out to determine the relationship between the angle of the ramp and its impact on the average speed of the car. And we found, in this case, that the increase in the angle of the ramp caused the average speed to be higher, right? And then you evaluate your hypothesis. So our hypothesis was supported by this data. And you want to support your statements with evidence. Now, you don't have to get into super detail on the conclusion or the report because you just did that in the analysis, but just a nice little wrap up. And just a note in general as we go forward here, quantitative data, that is numbers, is more convincing than qualitative data. I can give you descriptions. I can describe what happened. But if you can show me with numbers, if you can show me with a graph, if you can prove to me with data in the scientific community, that is seen as very weighty evidence. All right, so that is a good thing to provide quantitative data. So make sure that you're doing that in your analysis, and you might even refer back to it in your conclusion. All right, and then just wrap it up and say what your end result was. So I already described what our end result was. So to recap our lesson for today, we went over a couple things. We talked about what the independent variable is. That's the variable that you change. We talked about the dependent variable, which is the variable that we measure and see how the change in the independent variable affected that dependent variable. In our example for today, it was change the ramp angle in degrees, and we saw the impact on the change in the speed in meters per second, right? Control, we want to make sure that we're controlling every other variable that we're not investigating, that we're not measuring, because we want to have a methodical and quality experiment that we're conducting. Qualitative goes with qualities, that is descriptions or observations, that's that type of data. And quantitative data is data that includes numbers. So I don't have the definitions right here. You can always circle back in this lesson and go check them out, but make sure you fill out your notes just so you're tracking with us. And as we proceed with our activities this week, you're going to be using these terms, and you're going to be using the scientific method to both design and to carry out an experiment. So stay tuned. Until next time, this is Mr. Simkins in the Simkins Physics Corner.